Algebra 1, Investigation 10. This is all about taking our quadratic functions and seeing what happens when we transform them. How can we compare that to like when we transform our linear functions? So as you go through this, make sure that you pause the video at different points so that you can practice these before you actually see them from me. So we'll dive right in. A quadratic function is a function that can be written in this form, ax squared plus bx plus c, where a is not equal to 0. And we'll jump to this question on the left-hand side. It says, if a was 0, would the function still be quadratic? If not, what type of function would it be? Well, if I put f of x, and we would say that f of x and the a part of it is 0, well, we would be seeing something like this, 0x squared plus bx plus c. Well, that would just mean that the x squared part would be going away, and I would just have bx plus c. Well, it's no longer quadratic because we don't have a highest degree of 2. We have a highest degree of 1 right here, which means that it is linear. So, going on, in Investigation 6, those linear functions were graphed as transformations of our parent function f of x equals x. Similarly, we will graph a quadratic function with its parent function of f of x equals x squared. This is where we base all of our transformations, and when we stretch it or compress it, move it up or down, right or left, or reflect it, this is where we're starting. So it says complete the table of values for f of x equals x squared, and then we're going to graph that parent function. So when we do that, we are going to say, if I plug in -3, it would say something like this, f of -3 equals -3 squared. Now that entire -3 is being squared, so -3 times -3 is positive 9. Okay, f of -2 is -2 squared, so we would say -2 times -2 is a positive 4. Same thing with -1, we get -1 squared is 1, 0 goes to 0, 1 goes to 1, 2 goes to 4, and 3 goes to 9. So when we graph this parent function, we're going to see something like this. So on our coordinate plane, we're going to cross at 0, 0 with the y-axis. You could also do this with our procedure for graphing based on our vertex and plugging in other numbers. You'd still see that the y-intercept is 0, that the vertex is 0, and you would need other points anyways. And we get that at -1, 1, at -1, 1, at 2, 4, and -2, 4, and then at 3, 9. So up here at 9, and then -3, 9. And we see that this is our parent function. This means that this is what we base all of our transformations on. It's the original. It doesn't have any transformations on it, so that when we do have transformations, we can see what happens. So we'll do that right now. As is the case for the linear parent function, the quadratic parent function f of x equals x squared can be written as f of x equals ax squared, where a is 1. The graph changes when we have different values for a. So for example, number 1, this would be a good time to pause it and try this out for yourself. But we are going to graph y equals x squared and y equals 2x squared on the same set of axes. Compare the two graphs. So we have our original parent function, and then we're also going to graph f of x, or y, equals 2x squared. So I'm just going to make a little table here. You could, once again, do the vertex and the y-intercept, but it's going to end up that you're going to have to plug in other values anyways. So I'm going to plug in -2, -1, 0, 1, and 2. That will give me a good amount as far as the shape of my graph. So when I plug it in, I'm going to say y equals 2 times -2 squared. Well, I'm going to do the -2 squared first and get 2 times 4, which is a positive 8. I plug in -1 now. Y equals 2 times -1 squared. Well, -1 squared is 1, times 2 is 2. And we keep going. Plug in 0, I'm still going to get 0. Plug in 1, I'm going to get a positive 2. Plug in 2, I'm going to get 8. So when I go to graph this, I'll do it in a different color line. It'll be in green. We still have our y-intercept at 0, 0. But now when I go to 1, I'm already up at 2. And -1 is at 2. And then 2 is at a positive 8. And and negative 2 is at a positive 8. If you want to think about that axis of symmetry, it will be at this point x equals 0 for both of them. And you can see that it is symmetrical all the way around. So we have this new graph, okay? So when we look at it, what has changed? Well, we haven't changed the x-intercept or the y-intercept, so that hasn't moved. It hasn't moved up or down, right or left, but it has stretched out. So this is a dilation. We have actually dilated our function to be times 2. It's twice as big each time that we plug in our x value, and so it is a stretch here. Okay, so we have a dilation with a stretch. Okay, all right, we'll try it again with y equals x squared and y equals 1/2 x squared. Okay, and we want to put that on the same coordinate plane, so I'll do our parent function really quick here. 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, and negative 3, 9. Okay, so here is our parent function. We are going to compare y equals 1/2 x squared to it. And I'm going to do the same thing. Table of values. Once again, pause the video and try this out for yourself, see what happens. But I'm going to plug in negative 2, negative 1, 0, 1, and 2. All right, so when we plug it in, y equals 1/2 of negative 2 squared. Well, negative 2 squared is 4 times 1/2. Well, half of 4 is 2. Plug in 1. 1/2 of negative 1 squared. Well, that's a negative 1 squared is a positive 1 times 1/2 is 1/2. 0 goes to 0, 1 goes to 1/2, and 2 goes to 2. So I'll graph this in blue this time. And we still have our x-intercept, y-intercept at 0, 0. And then we have 1 goes to 1/2. So we're only up half a box. And the same with negative 1. And then negative 2 goes to a positive 2. And negative 2 goes to a positive 2. Now you could plug in other values to see even more of this graph, but you can already see that it's getting wider here. It'll look something like this. That'll be the shape of our graph. So if we compare it to our parent function, we would say, well, it's another dilation. A has been changed, which is another dilation. But in this case, instead of being a stretch, we would consider it a compression because it's wider than the parent function. All right, so that's number 2. And then we're going to graph y equals x squared and y equals negative x squared on the same set of axes. Once again, pause the video and try this out for yourself. And I'm going to do it on this page here. So our parent function, just like before, we would have this. All right, here is our parent function. And then we're going to compare it to y equals negative x squared. Okay, now I'll probably have enough room on this graph I will have enough room for negative 3, negative 2, negative 1, 0, 1, 2, and 3. I'll do this quick. So when we plug it in, we have y equals negative, and then we're plugging in the negative 3 and squaring it first before we use this negative out here. So I'm going to get y equals negative, and then the positive 9 coming from that exponent, meaning that we're going to get negative 9 here. I'll plug in a negative 2, and the same thing happens. That squared part is going to make the parentheses positive, so we have positive 4 here, but then our outside negative makes it negative, so negative 4. Plug in negative 1, we get negative 1. 0 goes to 0, and then it happens all over again. We get positive 1 in there, but it makes it negative, so we get negative 1, negative 4, and negative 9. So we plot this, and I'll give myself a little bit of room here. I'll plot it in, let's say, pink this time. So we still have an x, y intercept of 0, 0, but now we are going negative. So we have something like this. All right. So what has happened to this? Well, it's not any wider or it's not any more stretched out than our original parent function, but it does look like it's been reflected. And that's because it has. It's been reflected over the x-axis. That comes because of our a value. In this case, a negative 1 being our a value. So when we look back at this question, compare them, we would say, well, it's not a dilation, but it is a reflection for number 3. All right, so number 4, what is the effect of a on the graph of ax squared? Well, we can get a dilation if that's a particular number, and we'll talk about exactly what makes it a stretch or compression. And then it's also potentially a reflection based on if a is positive or negative. So let's talk about those particular values. I have them down here, and you hopefully have already made this connection. But when we have a stretch, so when it's skinnier than the original parent function, we would have an a value that is, especially, hopefully you caught this, if our a is greater than 1, then we would say it's a stretch. So if it's a bigger number than 1, 2, 3, 4, 5, or any of those decimals in between, it's a stretch. But this also happens when we have a number that is less than 1, so -2, -3, -4. These will both cause a stretch. If it's equal to 1 and equal to -1, we'll talk about that in a second, but it's not a stretch. It just has to be greater than 1, or it has to be less than 1. A compression then is the numbers that we aren't including here, so the numbers that are getting close to 0. You can think about it as absolute value, but you could also say all of the numbers that are between -1 and 1. So -0.75, -1/2, -1/3, or the positives, 1/3, 1/2, 3/4, whatever it might be. It has to be between -1 and 1 to be a compression. That will make it wider. And lastly, your reflection is pretty simple. A is less than 0. It needs to be a negative number to be a reflection. Well, I said, what if a is 1 or a is -1? Well, it's not going to be a stretch or compression. For a equals 1, this is the parent function. And if it's -1, well, then we would say this is still, it's not stretched or it's not compressed, but it's just a reflection. And yes, we can definitely have combinations of these. We can have reflection and we can have a stretch or compression. So let's look at number 5. How will the graph of 2/3 x change in relation to the parent function? Take a second to write down your thoughts on that. But based on our rules here, we would say, since 2/3 is less than 1, we would say this is a compression. Okay, it's going to be wider. Okay, it's not going to be stretched out like we would have if that 2/3 was greater than 1. And then number 6, how will the graph of -4x change? -4x squared change? Well, that -4 falls in this category. A is less than 1, so it must be a stretch. But it is also less than 0, so it must also be a reflection. Okay, so you can start getting a sense of what's going to happen with these before you even graph them based on that a value. Now we have another transformation that we can do on these. And we've been looking at ones that have just been crossing at our origin at 0, 0. And that's what's going to happen if we have f of x equals ax squared. It's always going to cross the y-axis at 0, 0. That's because our c value in ax squared plus bx plus c is 0. But what happens if we have f of x equals ax squared plus c, and that c is not just 0? So for example, number 7, graph the quadratic parent function and the function f of x equals x squared plus 1 on the same set. So pause the video, try that for yourself, and I'm going to show it right here. So we have our original parent function, of course. So I'll graph that. 0, 1, 1, 2, oops. A little bit too quick there. We should have our 2's at 4 and our 3's at 9. All right, here is our parent function. And then we are going to graph y equals x squared plus 1. So when we have our table, -3, -2, -1, 0, 1, 2, and 3, when I plot these, I'm going to say, well, y equals -3 squared plus 1. Well, -3 squared is 9, plus 1 is 10. -2 squared, well, -2 squared is 4 plus 1 is 5. -1 squared is 1 plus 1 is 2. 0 squared is 0 plus 1 is 1. And then we repeat all over again because our axis of symmetry is still that 0. So we have all of these. And I'll plot these in, let's say, red this time. So we have it a little bit different. We don't have 0, 0 as our x-intercept. We have it at 0, 1. And then our 1s are going to be up here at 2. Our 2s are going to be at 5. And our 3s are going to be at 10. So it looks a little bit different. Oops, sorry about that. It looks a little bit different, but not by a whole lot, because we actually still have the exact same shape as our parent function. It's not stretched or compressed, but it has just transitioned just a little bit up 1. So we have a translation here up 1. That's all that's happened, okay? And then you can try number 8 for yourself, x squared minus 2. I won't put the entire table here, but it's going to look something like this. If we have our original parent function here, okay, here's our parent function. If I have f of x equals x squared minus 2, my new function is going to be something like this. Same shape as before, but just down 2. It's been translated 2 units. Make sure that you try that and prove that for yourself, but we can make that assumption. If I have that c value being different, we can assume that it's going to be a translation up or down based on if it's positive or negative. So number 9 says, predict how will the graph of f of x equals x squared plus 7 compare? Well, it hasn't been stretched or reflected because a has not changed. It hasn't been stretched or compressed or reflected because the a hasn't changed, but our c value has. And the c value tells me that has moved up 7 units. Okay, this is a translation. Okay, so we're going to use a calculator now to predict how will these change in number 10 and 11. Now, down at the bottom here, I also have a couple more rules that we can go by, and we just talked about these two. Okay, if our k value, or in this case, what we've said so far as our c value has changed, it's a vertical change, a vertical transformation, up or down based on if it's positive or negative. Now, in the future, we will also look at these two, but I'll introduce them right now. What if if our function has something like this? Y equals x plus 2 squared, something like that. So the actual change, that plus amount, is inside of where we have our exponent. Well, this changes a little bit differently. I won't get too far into it because it does come up later. But funny enough, this will give us, even though it's a plus 2, this will give us a shift to the left 2 units. Okay? The reason comes because we have our quadratic function technically in the form, if you want to say it like this, y equals, I'll use their variables here, x minus h squared. And so whenever we have an h value that's negative, or what we would think of as left, let's say in this case a negative 2, so x minus a negative 2, when we see that plus value, since these end up being positive, we actually know that it's to the left. Okay, so a plus value inside of that exponent is going to go to the left, whereas if I had something like this, y equals x minus 3 squared would be 3 units to the right. Okay, so I just introduced that so that if that comes up somewhere, you know kind of what's happening. It's a little bit counterintuitive, but it comes because of our original form has a subtraction sign inside of our parentheses. So when it's a negative h value, it's going to go to the left, even though it looks like a positive when we put those negatives together. All right, so let's just finish with 10 and 11 on our graphing calculators. The first one has negative x squared plus 2. We're also going to compare this to the parent function, so I'm always going to graph x squared here. Okay, so when we do this, we're going to go to y equals, and I'm going to put in x squared first, so x squared, and then I'm also going to put our next function, negative x squared, and then let's see, we said plus 2 for this first one. Okay, so plus 2. So when we do zoom in 6, we can see our two functions here, and we can assume correctly that it's a reflection, which we can see there's no stretch or compression, but it has been moved up 2 from the origin. Okay, so you can see that with that red line. So we can say for this one, it's a reflection, and we have translated it up 2. Now you should be able to guess as far as this point with 11 and confirm it with your calculator for 1/2 x minus 3. So I'll go back and change it to 1/2 x squared minus 3. All right, so I'm going to change this one. So I'll use that 1/2 in parentheses just to make sure that it's used correctly, and then x squared and minus 3. Well, if you've been following along, that 1/2 is going to do something as far as a stretch or compression or a reflection. Since it's not negative, it's not going to be a reflection, but since it is less than 1, we would know that it should be a compression. And then that minus 3, that's a translation, down 3. And so let's see if we're right. And here's our parent function in red, in blue, and our red is our new transformation, and we do have it wider, so it is a compression, and the origin, it's down 3 from that origin. Okay, so we can see all of those transformations. All right. Well, from here you can hopefully get your investigation practice done pretty quickly as far as being able to know what is happening with the transformations. Well, I hope this helps for homework and for studying.